our last speaker for today is Yelena Mandelshtam, and she'll tell us about the combinatorics of m=1 Grasstopes.
Great, thank you. And thanks so much to the organizers for the invitation. So I'll tell you about joint work, which has this title. You want to find it on arXiv, and it's with Dmitrii, Pavlov, and Lizzie. Pratt. Lizzie is here, and you'll also hear from her on Friday. So I'll start with some definitions that we've heard several times today, but I'll go over them quickly again. So the Grassmannian, which we denote GRKN, I'm talking about the real Grassmannian. It parameterizes k-dimensional subspaces of n-dimensional space, or if you prefer to think about it as k-1 dimensional planes in n-1 dimensional projective space, you can do that as well. To quote my advisor, any vector space I've ever met has come with a basis. So I like to think of these as k by n matrices, which record the k basis vectors. But of course, you can choose different bases. So we want to mod out by left multiplication by GLK, which corresponds to changing the basis. And this embeds into n choose k-1 dimensional projective space via the Fluker embedding, which is just taking the k by k minors this. Oh, I found okay. The k by k minors, so the k by k subdeterminants that we can find here, indexed by a set I, which is it tells us which columns we're choosing. So for example, if I'm looking at the Grassmannian 2, 4, I can start with a 2x4 matrix. Most of the time we can reduce it to look like this. And then my minors will be, so this is in the order 1, 2, 1, 3, 2, 3, 1, 4, 2, 4, 3, 4. You can check that these are the determinants of the corresponding minors. And this will, so there's 4 choose 2, which is 6 of them. So this will live in 5-dimensional projective space. And as you can see here, not every point in 5-dimensional projective space can be written in this form, because there's a relation that holds between these minors, namely that AD minus BC is AD minus BC, which is written here. So this is the one Fluker relation we have in the Grassmannian 2, 4. In general, we'll have more of them that look something like this. All right, and then the positive Grassmannian, we take the part of the Grassmannian, which where we set all of the minors to be non-negative. So actually, this is called the totally non-negative Grassmannian, but positive is shorter to say. Okay, and so the amplituhedron is defined. So we saw this definition earlier today, but it's defined as the image of a map induced from a totally positive n by k plus m matrix. So we have parameters n, k, and m. Also that we heard about earlier today, where we map from the totally non-negative Grassmannian into smaller Grassmannian k plus m, where a subspace gets mapped to a new subspace that's given by multiplication by z, our linear map. And so, for example, when k equals 1, this map becomes very simple. So we start with, so when k is 1, we just have a map from projective space P n-1, but non-negative, since we're taking the non-negative part of the Grassmannian. So here we have a point here, A1 to AN, where all of these are non-negative. And then we multiply by our matrix Z, Z1 to Zn. And this, if we just multiply it out, it's the sum of the AI Zi, where all the AIs are non-negative. And so if we consider our Zi as points, then what we've written down here, okay, and we remember we're in projective space. So if we want to draw an affine picture, then we dehomogenize this. We can choose a dehomogenization, for example, one where we set the sum of all of the a's to be equal to 1. So then what we have here is the sum of ai, zi. The ai's are non-negative and they sum to 1. So what we've described is the convex hull of the zi's. In this case, since we're looking at the amplituhedron, we also have this restriction that z is totally positive. What that means is that these z's are cyclically ordered. So what we get is actually, so normally we'd get, if z was an arbitrary matrix, we just get the convex hull of the z, so it would still be a polytope. In this case, we get a very special polytope. We get a cyclic polytope. So these are very special polytopes. And I guess that tells us that this is a very special linear map. So in general, so here when k equals 1, what we have, the totally non-negative Grassmannian is a simplex. And when we take a linear map from the simplex, we get a polytope. When we take a totally positive linear map from the simplex, we get a cyclic polytope. And in general, so the amplituhedron, we're not starting with a simplex anymore. We start with a more complicated thing, the non-negative Grassmannian. So what we get has been called the next best thing to a polytope, the amplituhedron. All right, and now I'll define a Grasstope, which is in the title of the talk. So the name comes from Grassmann polytope, and the idea is, like I said, so a polytope comes from starting with a simplex and applying a linear map to it. Here, we're starting with a Grassmannian and applying a linear map to it. So it's like Grassmann polytope. And so it's the same definition as for the amplituhedron, except now Z does not have to be a totally positive n by k plus m matrix. But now I had to draw a dashed line. I lost the pointer, but there's a dashed line over there. Because the way I wrote this right now, there's no guarantee that this is a well-defined map everywhere on the entire non-negative Grassmannian. And so what I mean by that, so when we take a vector space and then we map it in this way, I'm expecting to land in this Grassmannian k plus m, but it's possible that one of these vectors actually gets sent to 0, and then I won't get something of the correct dimension over here. So this happens if my vector space has non-trivial intersection with the kernel of Z. And then my results will drop in dimension, which would make this map not defined on that point. So we say that the map Z tilde, which is induced from our linear map Z, is not defined on the set of vector spaces that have, in the non-negative Grassmannian, that have non-trivial intersection with the kernel of Z. And so it turns out for the amplituhedron, you don't have to worry if this never happens. It's always empty when Z is totally positive. But now a natural question is, when do we actually have to worry that this map is not well defined?
So one question like about notation. So your notation is G and KM, but it also depends on Z in very essential way.
Mm-hmm. Yes, this should say of Z. G and KM of Z. Thank you. Yeah, so the comment was that this should depend on Z, and it does. Okay. Yeah, so when are these well defined? So in 2016, Thomas Lamb showed that this condition, so there exists a k plus m by k matrix M such that all k by k minors of Z times M are positive, is a sufficient condition. So if this occurs, then the map Z tilde is well defined on the positive Grassmannian. And question was whether this is a necessary condition as well. So shortly after that, Stephen Karp provided a combinatorial characterization of well-defined maps. So a different one. And then Pavlov Goloshin showed that this condition 1 is not necessary. So there are cases where this is not satisfied, but Karp's condition is satisfied. So this inspired Thomas Lamb to propose a terminology. So if a matrix Z satisfies condition 1, which does still give us some meaningful information. So we know if it satisfies 1, then the map is well defined. But we also want to say that in some sense, it is better behaved than the ones that do not that are well defined but do not satisfy condition 1. So if it satisfies condition 1, it's called tame. If it does not satisfy condition 1, but it is still well defined, it's called wild. And so in our work, we decided to consider Grasstopes. Tame Grasstopes for m equals 1 had been covered by Williams and Kirk, but we wanted to study wild ones, and also we decided to study what we call rational Grasstopes, which are the Grasstopes when the map is not well defined everywhere. So even if the map has base points and it's not well defined everywhere, we can just throw out the points where it's not well defined and still consider the image. And so that's that image is what we call the rational Grasstope.
Rational is more general.
Yes. Well, yes. I guess when we say rational, we mean not well defined everywhere. So it's not really a generalization, but I guess we could just call all of them rational.
Okay. Well, why do you call it rational?
It's the image of a rational map. It's the image of a rational map.
Ah.
Yeah. All right. So, okay. So this proposition here, I guess we wrote down something that seemed to be understood by experts, but wasn't written down before. And this is kind of an interpretation of this condition 1, a geometric interpretation. And so we showed that a matrix Z satisfies condition 1, which means that the Grasstope is tame, if and only if there exists a hyperplane satisfying some conditions that is disjoint from the Grasstope. So in the hyperplane is in the ambient space of the where the Grasstope lives, the ambient projective space. And so when m equals 1, this condition here is irrelevant. And when m equals 1, we're saying that Grasstope is tame if and only if there exists a hyperplane in PK, which does not intersect the Grasstope. So what this means is that the Grasstope is tame if and only if we can draw its image in a bounded way in some affine chart of PK. So the Grasstope will live in PK. If it's tame, there's some disjoint hyperplane. So when we dehomogenize to draw in an affine chart, we can choose the disjoint hyperplane to dehomogenize with respect to, and then since our Grasstope never touches it, it'll be contained in this affine chart. And conversely, if it is not tame, then it intersects every hyperplane. So no matter which affine chart we pick, there will always be points at infinity. All right. So now I'll give another definition, the sign variation. So if we have some vector v, and we call the variation of v var v, the number of sign changes in v. So here we have 1, -1, 1, 2. This changes sign twice, from plus to minus and then to plus again. And we ignore zeros. So var of 1, 0, 1, 1, 0 is 0 because it just doesn't change sign. But var bar of v is the maximum number of sign changes when we are free to choose any value for the 0 that we in order to maximize the variation. So var bar of 1, 0, 1, 1, 0 is 3, because if both zeros are chosen to be negative, we go from plus to minus to plus, and then to minus again. But adding zeros to our vector doesn't necessarily change the var bar. Here we can see that both var and var bar of -1, 0, 1 is 1. So we can also, instead of writing actual numbers, we could just put pluses, zeros, and minuses and compute the variation that way. All right, so Karp and Williams wrote a paper called M=1 amplituhedron and hyperplane arrangements, where they studied the M=1 amplituhedron. So since M=1, we're mapping from the positive Grassmannian Kn to the Grassmannian k+1, which we can think of as p to the k. So if p is 2, we can draw nice pictures. Sorry, if k is 2, we can draw nice pictures. And this is a paraphrased version of a theorem from this paper. So the M=1 amplituhedron consists of the closure of the bounded regions of the hyperplanes corresponding to rows of Z. So I'll explain how you get hyperplanes corresponding to rows of Z. But for now, if you just trust me that we can write hyperplanes that correspond to rows of Z, then we draw them. So this is a picture when k = 2. And then this will make 3 bounded regions here. So this is a 2×4. Sorry, n is a 3×4 matrix. So we have four lines. We'll have 3 bounded regions, and those make up our M=1 amplituhedron. This is part 1 of this theorem. Part 2 is that the bounded regions can be labeled according to signs. So the hyperplanes that correspond to rows of Z also have orientations. When Z is a totally positive matrix, it's a cyclic hyperplane arrangement, and we have so the orientations will always look like this. And then we can write down the sign vectors with respect to these orientations. So for example, this region right here is on the plus side. Each arrow is pointing towards it. So this will be plus, 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 plus. And then this one is pointing, each arrow is pointing away from it except for the last one, which is pointing towards it. This is minus, 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 plus. And then the bounded regions are exactly the ones whose sign vectors have var at least k, which is, in this case, is 2. So indeed, these 3 regions have 2 sign changes, and the others have 1 or fewer, or 0. All right, so we have this characterization for the M=1 amplituhedron, and these results also hold for the case of tame Grasstopes. So if Z is not necessarily totally positive, this will no longer be a cyclic hyperplane arrangement, but we still have some hyperplane arrangement. We have we can write down the sign patterns, and the tame Grasstope will consist of the bounded regions of those hyperplanes. So we wanted to study M=1 Grasstopes. So yeah, sorry to the physicists. I guess this is the M that is always 4 when you're talking about physics, but in this talk, M is always 1. Okay, so now I'll explain what it means, or how we get these hyperplanes that correspond to the rows of Z. So before we do that, just review some projective geometry basics. So a question, so if we're given a hyperplane Y in GRK k+1 in Plucher coordinates, so that means we take all, so this is a k by k+1 matrix, we take its k by k minors, and then we get a k+1 vector in PK. So if we have this representation of a hyperplane given by a point in PK, how can we write down the equation of the hyperplane? So I'll give you the answer for k = 2. So Y is the span of 2 vectors, V and W. and a point X lies in the hyperplane Y, if and only if this determinant, where we write down X and then the two vectors that span Y, vanishes. And so we can then expand this determinant and write down the equation of the hyperplane. So when I write P23, I mean the 2,3 minor of the matrix that represents this hyperplane. So we have x1 times P23 minus x2 times P13 plus x3 times P12 is equal to 0 when this determinant vanishes. And this is exactly the equation of the hyperplane in terms of the values of the Plucker coordinates for the hyperplane. But the Plucker coordinates will generally be given P12, P13, P23. So we've reversed the order and put alternating signs on them. And in general, it's the same exact thing. You can write it down. We get it by doing similar Laplace expansion of a determinant like this. And we get this equation for the hyperplane. And again, it's if you start with your minors in reverse lexicographic order, you reverse the order to match, those are your coefficients are this in reversed order with alternating signs. So then if we take a point in P2, then this corresponds to, so this point 1 minus 1, 2 in P2 corresponds to the line z plus y plus 2x equals 0 in P2 dual. And then if we wanted to draw this picture, and we could dehomogenize with respect to x, and then the line looks like y plus x plus 2 equals 0 in R2. Okay, so then we can, maybe I'll go back. So then we can do this. So when I say that our rho corresponds to a hyperplane, I mean, we consider the rho as a point in P2, and then we actually just write down its dual in this way. Okay, and now our main theorem is, so it's an analogous statement to the theorem about the amplituhedron and tame Grasstopes. So just minus the bounded condition. So for z with trivial base locus, so well-defined, the Grasstope G and K1 of z consists of all regions whose sign vectors have bar bar, at least k, with respect to the hyperplanes defined by the rows of z. I forgot to mention that this might remind you of twistor coordinates if you're familiar with them. And indeed, these are twistor coordinates, and we can and do rephrase this in terms of twistor coordinates in our paper.
Is it for big case?
This is for wild and tame.
Wild.
So well-defined. And then, yeah, so the tame case, just these regions are also all bounded. In the wild case, it's necessarily not true that they're all bounded because the Grasstope is, because that was the corollary of your slide.
In case, the difference is that they are bound, exactly bounded regions.
Yeah.
In the general case, it's the same.
Yes, in the general case, we keep this sign flip characterization, but no boundedness anymore. Okay, and so, for example, here we have a wild a matrix Z that gives us a wild Grasstope. We can write down, oh yeah, okay, and I guess, okay, so we can write down these lines that we get. So I guess this one, for example, will be 0z minus y, 0x, just minus y. And then we choose a special dehomogenization that allows us to see the picture nicely. Just and then so these are our linear forms. So even though this line, if we just drew the line, it would be the same as if the x didn't have a minus, we actually do care about the minus because that's what gives us the orientations of our hyperplanes. So now we will also draw an arrow on each hyperplane pointing to where it is positive. So replace this with a greater than or equal to, replace this with a greater than or equal to 0 here, and then the arrow will point in that direction. So we can draw these 6 lines from the previous slide with the arrows. And then we can label them with sign patterns. And then all of the ones that have at least 2 sign changes are going to be contained in our Grasstope. So like this region, for example, the ones that have less than 2 will not, like this one, which has 0, or this one, which has 1. So now we can shade in all of the ones that have at least 2 sign changes. So this is what our wild Grasstope looks like. And so this right here is actually not a point. There is a tiny region there. But you can see actually that there's no line that does not intersect this Grasstope. Yeah.
For regions, do you also care about like edges since you're using big values?
Yes, exactly. So yeah, so in particular, it is closed. So this theorem guarantees that because we're using bar, this theorem guarantees that our Grasstope is always closed.
So is it always kind of the whole?
In this wild case.
Like in tame, I guess it's since it's universal.
Yeah, tame is,
it should be the whole.
yes,
The wild case it's also true.
I think so. I think I'm not lying right now. Okay. But so I guess I will give a short proof sketch for this. So the way that it works, so we identify our ambient space PK with hyperplanes in P to the n-1. And the way we do this, so we map, so point in PK goes to a point in Pn-1, and then this represents a hyperplane in this way, not in the same way as I explained a few slides ago. And then we have kind of 2 components. So one is that a hyperplane in Pn-1. So we identify a PK with hyperplanes in Pn-1 that contain the kernel of Z. So this, you can check that the dimensions actually match up this way. And so containing the kernel of Z kind of means that we are points that could be mapped from the Grassmannian into this, into PK. And then we show that this hyperplane in P to the n-1 contains a positive k-dimensional subspace if and only if bar of the point U corresponding to the hyperplane, so it's a dual point, is at least k. And this basically just comes easily from a result of Guntmacher and Krein, some mathematical physicists that were the very early study years of positivity. And then also, so the second part is that a hyperplane contains a positive k-dimensional subspace if and only if the point X that it came from is in the Grasstope. And what allows us to do this is that if, so H, a hyperplane that contains both the kernel of Z and a positive k-dimensional subspace. Well, so we know that the kernel of Z, because our map is well defined, the kernel of Z has to be disjoint from the positive Grassmannian. So in particular, sorry, this is, okay, so not just the positive Grassmannian, it has to be disjoint from any positive subspace. So if it contains both the kernel and the positive subspace, then we know that the point X actually is the result of mapping the positive subspace that it contains. So actually a point from the positive Grassmannian through Z into this PK. So it was very important here that the map is well defined. And I did mention that we also wanted to study rational Grasstopes. So this was, so we couldn't do exactly the same thing. We couldn't prove the same result, but we were able to prove a weaker version of it. So if Z has non-trivial base locus, so that means that there are points in the positive Grassmannian that do intersect the kernel of Z. The rational Grasstope contains all points such that var bar is, sorry, not var bar, just var is at least K. So, and it is contained in the set of points with var bar at least K. So what this means is that all of the points in the interiors of these regions where we don't have zeros, they are all contained in our rational Grasstope. The only question mark is on the boundaries that have zeros. And the way that this works is that here, so it's a similar idea, except here, when it contains a positive k-dimensional subspace, if we add an additional positivity, so when we say use var instead of var bar, we get some strict inequalities rather than non-strict inequalities. And we're able to use those to actually wiggle the positive k-dimensional subspace we have. So perturb it a little bit, and then perturb it a little bit. And then we actually do show that we can get a positive subspace that is disjoint from the kernel. So that's why we get this var result, but the var bar result, we actually are not sure in general what happens on the boundary. So this is an example of a rational Grasstope. And we actually just checked manually that all the points, so this one is actually closed, all the points on the boundary are included. And we actually don't have any example where not all points on the boundary are included. I think there are some special conditions that need to be satisfied for that to happen, but we didn't study that extensively. But the interesting thing about this example is that this topologically is a Mobius strip. Because I guess if you remember, we're in projective space, this region is the same as this region. But then when they get glued together, it gets twisted. So this one is not contractible and not a ball, therefore. So rational Grasstopes can behave pretty differently from well-defined ones, from tame and wild ones. And definitely there's more interesting things to study here. Okay, so now I'll move on to some combinatorial questions that are motivated by this study. So one question we can ask, so I guess now the way that we can easily get Grasstopes is we just draw a hyperplane arrangement, give them orientations and an order, and then we can just write down the sign vectors and fill in the regions with the correct sign variation. But you can see even if we pick the same lines, but we just switch the arrows on three of them, or I guess one of them, then you can get different numbers of regions in the Grasstope. So this one has 3 regions. This one has 4 regions. So these 2 bounded ones and then 2 unbounded ones that match up. And so we know that we can get different numbers of regions. So in the amplituhedron, it's a constant number of regions, but in general, we don't know. But we can get some naive bounds. So at least in this case, we can see that 3 or 4 are the only possible numbers of regions we can have, because the number of sign vectors with variation at least 2 is 4. The total number of regions is 7. And the total number of sign vectors is 8. So we get 16, but then we can multiply by -1, and it's the same sign vector. So it's 8. So the one sign vector that is missing could either be one of these or not. So that way we get either 3 or 4. of these represented among our sign vectors. And so in general, we can come up with naive bounds, like 3 or 4. But first we need to know how many regions are in a hyperplane arrangement. So fortunately, this was studied by Zaslavsky. So here I should say I'm talking about generic hyperplane arrangements. So for a generic affine hyperplane arrangement, we have formulas for the number of regions, that's R of n, and bounded regions, B of n. And so any projective hyperplane arrangement induces an affine arrangement with, if we dehomogenize, and we can dehomogenize away from intersections of hyperplanes. And so then if we do that, then we get an affine arrangement with the same number of, so any bounded region in our hyperplane arrangement is a region of our projective hyperplane arrangement. But now the unbounded regions of the affine arrangement, if we want to go back to the projective hyperplane arrangement, they'll be in pairs that match up. So our number of regions in our projective hyperplane arrangement will be the number of, so Bn plus Rn minus Bn over 2. So all the unbounded regions matched up in pairs. And so this is the number of regions, possible regions we're working with. So this is actually a naive upper bound for how many regions we'll have in a Grasstope. So maybe the Grasstope actually just covers all of PK. Another upper bound is the total number of sign vectors that have variation at least k. So whatever the minimum of these two is an upper bound. For a lower bound, we could get it's the total number of regions minus the number of sign vectors with low variation. So if we have all of these sign vectors represented, then whatever's left has to have variation at least k, and then is in the Grasstope. So once we have these naive bounds, we might ask if these bounds are actually attained. And so we gathered some preliminary data answering this question for some k and n. So we used a database of oriented matroids of rank k on n elements. And then, so what we did was we looked at each of these oriented matroid isomorphism classes corresponds to some hyperplane arrangement. And then within that class, we can reorder and reorient the hyperplanes. And so for each isomorphism class, we looked at all the reorderings and reorientations and looked at the upper and lower bounds for the number of regions in it. And actually for all of these values, it turned out that the maximum and minimum didn't depend on the isomorphism class. So so for 2,6, you draw 6 lines, however they are, and then there's always a way to reorient them to get only 10 regions or to get 16 regions. And you can also check that the minimum and maximum in these columns actually correspond to the naive bounds that we have from the slides before. So 3,7 is the first value that's not in this table, and that's because there it actually does. So the maximum does depend on which isomorphism class you pick. So actually the only one that attains the maximum is when you pick the cyclic arrangement and do some reorderings. So actually another interesting thing, so the minimum is attained by the amplituhedron, always. And in our experiments, the maximum, so in general, it's in these situations, it's always attained by every isomorphism class. But for the ones where it is not, where it does depend on the isomorphism class, maximum was always attained by also starting with an amplituhedron arrangement, so a cyclic hyperplane arrangement, and then just doing a reorientation of some of the hyperplanes. So for example,
so is it true that in case it's
I believe so, yes. Because it's the bounded region for generic, yeah. It's just the number of bounded regions. All right, so here's an example of attaining the maximum. So here, if we pick this is k equals 2, n equals 6, so we have 6 lines, and we start with a cyclic arrangement. But now, so all we do, we don't reorder anything, so it's still 1, 2, 3, 4, 5, 6, but we just switch the 2 and the 4 to face in the opposite direction. Then you can actually see that every single region has at least 2 sign changes. And so the Grasstope is actually all of P2 here. And so, yeah, a question is it true in general that the maximum is can always come from doing something like this? All right, so just some concluding remarks. So I guess hopefully I've convinced you that Grasstopes are at least mathematically interesting, and we even though we've dropped the positivity condition on the matrix Z, we still get lots of nice combinatorics and structure from just the one positivity condition that comes from us starting with the positive Grassmannian. There are open questions even for m equals 1, but of course it would also be interesting to look at higher m. And then, so a question for maybe the physicists in the room is, could there be a physical interpretation for general Grasstopes? And then, yeah, so as I said, for higher m, so maybe 4, so that to make the physicists happy. So it seems like they need to be, so in this project with m equals 1, it turned out that we could attack in very similar ways to the m equals 1 amplituhedron in the tame Grasstope's case, because the positivity of Z actually didn't turn out to be so vital in a lot of the proofs, but just based on some short exploration of higher m, it looks like we'll need some completely different methods to study Grasstopes rather than amplituhedra. And then also, I think it would be interesting to study Grasstopes that arise from other positive Grassmannians. So I guess later this week, we'll hear about the tropical amplituhedron. So tropical Grasstopes could also be an interesting direction. The orthogonal positive Grassmannian, symplectic positive Grassmannian has been studied a little bit. Maybe it would be interesting to consider Grasstopes from there. And yeah, that's all I had. Thank you for your attention.